The universe is stretching itself apart. The space between galaxies grows larger every moment, not because they are flying away, but because the very fabric of reality is expanding. This is not science fiction. It is the foundational truth of our cosmos, and it leads to consequences more bizarre than any fantasy. By the end of this journey, you will see the night sky in a completely new way. We will uncover why most of the cosmos is invisible, how we can hear echoes of creation, and what fate this relentless expansion has written for everything that exists. What single idea about the universe most fills you with wonder? This cosmic stretch is the first and most crucial fact to grasp, yet it is also one of the most commonly misunderstood. The universe is expanding, but it is not exploding. There is a profound difference. Picture not a bomb blast in the emptiness of space, but the emptiness itself being the thing that is changing. Galaxies are not hurtling away from each other like fragments of cosmic shrapnel through a static void. Instead, the very fabric of space, the stage upon which everything exists, is stretching. The distance between points in that fabric is increasing. A helpful way to visualize this is to think of dots drawn on the surface of a partially inflated balloon. As you blow more air into it, the balloon expands. Each dot does not move across the surface to a new location. They stay where they are, but the rubber between them stretches, making every dot drift farther away from every other dot. The galaxies are like those dots. They are embedded in the stretching canvas of space-time. This revelation did not come from pure theory. It came from a man peering through a telescope in the 1920s. Astronomer Edwin Hubble was meticulously measuring the light from distant galaxies when he noticed something peculiar. Their light was shifted toward the red end of the spectrum. This redshift is similar to the Doppler effect you hear when a siren from a passing ambulance drops in pitch as it moves away from you. The sound waves get stretched. For light, that stretching means a shift toward red. Hubble found that the farther away a galaxy was, the greater its redshift. The only logical explanation was that these galaxies were all moving away from us and from each other because the space they reside in is expanding. This single observation shattered the old idea of a static, unchanging universe and launched the field of modern cosmology. It told us the cosmos had a beginning, and it has been growing ever since. But if space itself is stretching, what does that stretching do to the light traveling through it for billions of years? Hubble's discovery of that universal redshift was the first real measurement of the cosmos in motion. It gave us a tool, a cosmic speedometer, to gauge not just that the universe is expanding, but how fast. That stretching of light to longer, redder wavelengths is our most direct evidence. Think of a wave drawn on a rubber band. If you hold both ends and slowly pull, the wave stretches out. Its peaks and troughs get farther apart, the wavelength increases. Light is a wave, and as it journeys across the expanding universe, the space between its peaks is stretched by the very expansion of the fabric it travels through. This is cosmological redshift. It is subtly different from the more familiar Doppler shift of a passing siren. The siren's sound waves are compressed or stretched because the source is moving through the air. For cosmological redshift, the source, the galaxy, is roughly stationary in its local space. It is the space between us and the galaxy that is growing, stretching the light during its multi-billion-year journey. Astronomers measure this with incredible precision using instruments called spectrometers. They break the light from a galaxy into a rainbow-like spectrum. Embedded in that spectrum are dark lines like unique fingerprints corresponding to specific elements like hydrogen or helium. We know exactly where these fingerprint lines should be in a laboratory on Earth. When we look at a distant galaxy, we find those same fingerprint lines, but they are all shifted toward the red, longer wavelength end of the spectrum. The amount of that shift tells us everything. A greater redshift means the light has been stretched more, which means it has traveled through more expanding space. which in turn means the galaxy is farther away and receding faster. This relationship is so reliable that redshift has become the primary yardstick for mapping the universe's large-scale structure. By measuring redshifts for thousands upon thousands of galaxies, we have constructed three-dimensional maps of the cosmos. These maps reveal the vast cosmic web, great filaments and walls of galaxies surrounding immense voids, all traced out by the reddening of their light. It is a map written in light, a historical record of expansion encoded in every photon that reaches our telescopes. But if we can measure how fast galaxies are moving away, the next logical question is to run the film backward. What happens when we rewind this expansion to its beginning? Running the cosmic film backward leads to a stunning and inevitable conclusion. All those galaxies racing away from each other must have been much closer together in the past. Rewind far enough and you reach a moment of unimaginable density and temperature, a singularity from which space and time themselves emerged. This is the Big Bang, the beginning of our expanding story. But the key to understanding that story lies in a deceptively simple mathematical relationship discovered by Edwin Hubble. It is called Hubble's law, and it states a profound truth about our cosmos. The farther away a galaxy is, the faster it appears to be moving away from us. This is a direct, linear relationship. For example, a galaxy twice as far away as another is receding at twice the speed. A galaxy 10 times farther away is receding 10 times faster. This relationship holds true for all galaxies in our local universe, painting a clear picture of a cosmos expanding uniformly in all directions. The number that defines this relationship is one of the most important in all of cosmology, the Hubble constant. Its current best value is approximately 70 kilometers per second per megaparsec. Now, let us unpack what that actually means. A megaparsec is an almost incomprehensible unit of distance, about 3.26 million light-years. So, for every 3.26 million light-years a galaxy is from us, its speed away from us increases by 70 kilometers per second. A galaxy 100 megaparsecs away, or over 326 million light-years distant, would be receding at about 7,000 kilometers per second. This number, the Hubble constant, is quite literally the current expansion rate of the universe. It is the speedometer reading for the cosmos. Determining its precise value has been one of the great quests in astronomy, because it tells us not only how fast the universe is growing now, but also its age and its ultimate fate. A higher constant means a faster expansion and a younger universe. A lower constant suggests a more leisurely expansion and an older cosmos. The journey to pin down this number has been fraught with debate and revision, leading to one of the biggest puzzles in modern science. But for now, this linear rule, this clean proportionality between distance and speed, gives us our first reliable map of the cosmic flow. It confirms that we are not at the center of some strange exodus. From the perspective of any galaxy in the universe, all others would appear to be fleeing in the same pattern. The entire fabric is stretching, carrying every point away from every other point. This uniform expansion is the signature of the Big Bang, echoing forward through time. Yet, if the expansion is so uniform, why does the cosmos look so lumpy, with galaxies clustered together instead of spread evenly apart? That uniform expansion from a single, dense origin seems to demand a central point, a location where it all began. This is where our everyday intuition betrays us completely. The Big Bang was not an explosion that hurled matter out into a pre-existing, empty space. There was no outside for it to explode into. Instead, it was the rapid emergence and expansion of space and time themselves from a state of extreme heat and density. To grasp this, we must abandon the image of a cosmic firecracker detonating at some spot in the void. The correct, though mind-bending, picture is this. The entire universe, all of space, was compressed into that initial hot, dense state. The Big Bang was the moment that space itself began to stretch and cool. This means it happened everywhere at once. The entire observable universe, every point we can see from Earth to the most distant galaxy, was once packed into that same unimaginably small volume. So where was the Big Bang? It was right here and over there and everywhere. Every location in the cosmos can equally claim to be the center of that expansion because every location was part of the initial conditions. A useful, though imperfect, analogy is the surface of an inflating balloon again. The dots on the surface represent galaxies. As the balloon inflates, every dot moves away from every other dot. Now ask yourself, where on the surface of that balloon is the center of the expansion? There is no center on the two-dimensional surface itself. The center exists in a third dimension, which the surface-dwelling dots cannot perceive. For our three-dimensional universe, the center of the Big Bang expansion would exist in a higher dimension we cannot access. From our perspective within the universe, the expansion has no center. It simply is happening uniformly everywhere. This is why astronomers observe galaxies receding from us in all directions, with more distant ones moving faster. It is not that we are at some privileged central point being abandoned. From any other galaxy, the view would be identical. The fabric of reality is stretching, and we are all embedded within it, carried along as the distances between landmarks grow. The entire universe, in a very real sense, is still the epicenter of its own ongoing creation. The uniformity of the cosmic expansion presents a profound puzzle. If the Big Bang was a singular, searingly hot event, why didn't everything just fly apart into a perfectly smooth, featureless mist of particles? The answer is etched into the oldest light in existence. If you could tune an old-fashioned television to static between channels, about 1% of that fuzzy snow is not random noise. It is the faint, cosmic whisper of creation itself, a glow that has been traveling for over 13 billion years. This is the cosmic microwave background, the CMB, and it is the single most important piece of evidence we have for the Big Bang. It is the afterglow of the universe's fiery birth, cooled and stretched by eons of expansion into the microwave part of the spectrum. To understand what we are seeing, we must travel back to a time before stars, before galaxies, before atoms as we know them. For the first several 100,000 years after the Big Bang, the universe was an opaque, seething plasma of protons, electrons, and light. Photons, particles of light, could not travel freely. They were constantly bouncing off the dense soup of charged particles, like someone trying to walk through a crowded, bustling room. The universe was a blinding, hot fog. Then, about 380,000 years after the beginning, a monumental change occurred. The expanding cosmos had cooled enough for electrons and protons to finally combine and form neutral hydrogen atoms. This event is called recombination. Suddenly, the charged particles were bound together and the fog lifted. The photons which had been trapped were finally set free. They streamed outward in every direction, and the universe became transparent for the first time. That first burst of liberated light is what we detect today as the CMB. It is a snapshot of the infant universe frozen in time. But the expansion of space has done something remarkable to that light. Over billions of years, the stretching fabric of the cosmos has stretched the light waves themselves. The once brilliant, visible light has been redshifted all the way down to much longer, lower energy microwave wavelengths. It has cooled from a temperature of thousands of degrees to just 2.7 degrees above absolute zero. This is why we perceive it as a faint, cold microwave glow coming uniformly from every point in the sky. Its near-perfect uniformity was a stunning confirmation of the Big Bang model, a relic of that initial hot, dense state. Yet when scientists examined this glow with exquisite precision, they discovered something even more revealing. The CMB is not perfectly smooth. Embedded within its uniform C are tiny variations, minuscule hot and cold spots, fluctuations in temperature of just 1 part in 100,000. These are the cosmic seeds, Those faint ripples in the ancient light are the imprints of the very first density fluctuations in the early universe, the gravitational blueprints from which everything we see today would eventually grow. The slightly denser patches, seen as slightly cooler spots in the CMB, had a little extra gravity. Over cosmic time, they pulled in more matter, eventually collapsing under their own weight to form the first stars, the first galaxies, and the vast cosmic web of structure we observe now. Every galaxy cluster, every filament, every void in our modern universe can trace its origin back to a specific pattern in that primordial microwave light. The CMB is our ultimate time capsule, a baby picture of the cosmos, and it tells us the universe was born with the specific imperfections necessary to build a world of wonders. But if this ancient light gives us a map of the universe's infancy, what does it tell us about the ingredients that make up the cosmos? Those faint ripples in the cosmic microwave background did more than just map the seeds of galaxies. They also provided the first definitive inventory of the universe's contents, and the results were utterly shocking. The matter that makes up everything we can see and touch, every star, every planet, and every living thing, accounts for a mere 5% of the cosmos. The other 95% is invisible, a dark and mysterious realm that governs the fate of everything. This is perhaps the most humbling discovery in all of science. We are not just a small part of the universe, we are made from a rare and exotic ingredient in a cosmic recipe dominated by forces we cannot see. The first of these invisible components is dark matter. It makes up roughly 27% of the universe. We know it exists not because we see it, but because we see its immense gravitational pull. In the 1930s, astronomer Fritz Zwicky was studying a giant cluster of galaxies and noticed something bizarre. The individual galaxies were moving so fast that the cluster's own gravity, based on the visible stars and gas, should not have been strong enough to hold them together. The cluster should have flown apart. Zwicky concluded there must be a huge amount of unseen matter, which he called dunkel materie, or dark matter, providing the extra gravitational glue. Decades later, Vera Rubin observed a similar mystery within single spiral galaxies. Stars at the outer edges of galaxies orbit just as fast as stars near the center, which defies the laws of gravity as we understand them. If a galaxy were only made of the stars we see, those outer stars should be moving much more slowly, like planets farther from the sun. The only explanation is that each galaxy is embedded in a vast spherical halo of invisible matter, a gravitational scaffold that extends far beyond the luminous disk. This dark matter does not emit, absorb, or reflect light. It interacts with ordinary matter almost solely through gravity. We can map its distribution by watching how its immense mass bends the light from more distant galaxies, an effect called gravitational lensing. These observations reveal a cosmic web of dark matter, an invisible skeleton upon which the visible universe is built. But if dark matter's gravity pulls things together, holding the cosmic structure intact, there is an even more dominant and stranger force working in the opposite direction. Dark energy is the true master of the cosmic expansion. While dark matter's gravity pulls the cosmic web together, a far more powerful and enigmatic force is working to tear it apart. This force was discovered in the late 1990s, and it overturned our most fundamental assumptions about the universe's fate. Until then, cosmologists believed the expansion of the universe was gradually slowing down. The collective gravity of all matter, both visible and dark, was thought to be acting like a cosmic brake, gently pulling on the fabric of space to decelerate its stretch. The big question was whether that gravitational pull was strong enough to one day halt the expansion entirely, leading to a cosmic recollapse, or whether the universe would simply coast forever, expanding at an ever-slowing rate. Two independent teams set out to measure this deceleration by observing distant supernovae, the brilliant explosions of dying stars. They used these stellar explosions as standard candles, cosmic mile markers, to gauge distances across vast stretches of the universe. By comparing how far away these supernovae were to how fast they were receding, they could chart the expansion history. What they found sent shockwaves through the scientific community. The most distant supernova, whose light had been traveling for billions of years, were fainter than expected. This meant they were farther away than the standard model of a slowing expansion predicted. The only possible explanation was that the expansion of the universe was not slowing down at all. It was speeding up. Some unknown repulsive force, stronger than the collective gravity of all the cosmos, was actively stretching space apart at an accelerating rate. This discovery earned the teams the Nobel Prize and introduced the world to dark energy. Dark energy is not a substance like dark matter. It behaves more like a property of empty space itself, a constant energy density infused into the very vacuum. A helpful, though imperfect, analogy is to think of space not as a passive stage, but as a springy foam. Imagine every single cubic centimeter of that foam has a tiny, intrinsic energy that makes it want to push outward to expand. Now, as the universe grows, you are not just adding more cubic centimeters of passive foam. You are adding more cubic centimeters of this springy, expansive foam. The more space there is, the more of this repulsive push you get, leading to a runaway acceleration. This is why the expansion began to accelerate around 5 billion years ago. Before that, the universe was smaller and denser. The gravitational pull of all the matter packed into a smaller volume was strong enough to dominate, causing the expansion to decelerate. But as the universe expanded, matter thinned out, diluting its gravitational influence. Meanwhile, the repulsive effect of dark energy, tied to the volume of space itself, grew stronger. About 5 billion years ago, the scales tipped. Dark energy's push overcame gravity's pull, and the expansion of the cosmos began to accelerate. Today, dark energy constitutes about 68% of the total energy budget of the universe. It is the dominant component, the driver of cosmic destiny. We do not know what it is. It could be a cosmological constant, as Einstein once proposed and then discarded, or it could be a dynamic field that changes over time. What we do know is that its relentless push is writing a cold, lonely, and expansive future for everything that exists. That acceleration is not a gentle nudge. It is a cosmic stampede, and its discovery was one of the greatest surprises in the history of science. For decades, the central question in cosmology was a simple one. Will the universe expand forever, or will gravity eventually pull it all back together in a big crunch? Everyone assumed the answer hinged on measuring how much the expansion was slowing. The collective gravity of all the galaxies pulling on each other across the void had to be acting as a brake. Two teams set out in the 1990s to measure this deceleration with precision. They focused on a specific type of stellar explosion called a Type 1, a supernova. These are thermonuclear blasts that happen when a white dwarf star steals too much material from a companion. The beauty of these explosions is their consistency. They always reach about the same peak brightness, making them perfect standard candles. By measuring how bright they appear from Earth, astronomers can calculate their true distance with remarkable accuracy. Simultaneously, by measuring the redshift of the galaxy hosting the supernova, they know how fast it is receding. By comparing distances and speeds for supernova both nearby and extremely far away, the teams could chart the expansion rate over billions of years. They were looking for the signature of a slowdown. The most distant supernova, whose light had been traveling for over half the age of the universe, would reveal how much faster expansion was in the past compared to now. The results, published in 1998, were not just unexpected, they were paradigm-shattering. The distant supernova were fainter than they should have been. This meant they were farther away than any model of a slowing expansion could explain. The only possible conclusion was staggering. The expansion of the universe was not slowing down at all. It was speeding up, some mysterious repulsive force counteracting gravity on the largest scales was actively pushing the cosmos apart. The two teams, one led by Saul Perlmutter and the other by Brian Schmidt and Adam Rees, had independently reached the same earth-shaking conclusion. Their discovery was so revolutionary it earned them the Nobel Prize in Physics in 2011. Overnight, the cosmic narrative changed. The universe was not merely coasting on the momentum of the Big Bang. It was being propelled by a hidden driver, a force we now call dark energy. This was not a minor adjustment to the model. It was a complete overturning of our expectations about cosmic destiny. The hunt for the brake had instead found the accelerator permanently pressed to the floor. Dark energy's accelerating push creates a boundary we can never cross. This is the edge of the observable universe, a fundamental limit to our cosmic vision. It is not a physical wall or a barrier in space. Instead, it is a horizon defined by time and the finite speed of light. In the 13.8 billion years since the Big Bang, light has had a limited amount of time to travel. The observable universe is the immense spherical region of space from which light has had just enough time to reach our telescopes. Every photon that strikes our detectors, from the Sun to the most distant galaxy, has been on a journey that began within this sphere. The radius of this observable sphere is not simply 13.8 billion light-years, however. That would be the case if the universe was static, but space has been expanding during the entire journey of that ancient light. The galaxy that emitted a photon 13 billion years ago is now much farther away because the space between us and it has stretched tremendously. When we account for this relentless expansion, the current distance to the edge of our observable universe is about 46.5 billion light-years. We are at the center of our own observable universe, and every other observer on a planet in a distant galaxy is at the center of theirs. Each sees a different sphere of visibility, a unique cosmic horizon. But what lies beyond our horizon? There are undoubtedly more galaxies, more stars, more of the cosmic web stretching far into the distance. The universe is almost certainly much larger than the part we can see, perhaps even infinite. Yet, those regions are forever lost to us. The space between us and those ultra-distant galaxies is expanding so fast, driven by dark energy, that light emitted from them today can never reach us. The photon sets out on its journey, but the finish line is receding faster than it can travel. It is like a swimmer trying to cross a river that is widening faster than they can swim. They will simply never reach the other side. Those galaxies have therefore passed beyond our cosmic event horizon. They have faded from view not by moving away through space, but by the space between us growing at an insurmountable rate. This means the observable universe is not a fixed entity. It is actually shrinking in terms of the number of galaxies we will ever be able to see. As more and more galaxies cross that invisible threshold and vanish beyond the horizon, our island of visibility will grow darker and more isolated over trillion-year timescales. But if we can never see beyond this horizon, how can we possibly know anything about the universe as a whole? The geometry of the universe is written into the fabric of space itself, a cosmic shape determined by the total amount of matter and energy it contains. Based on the precise measurements of the cosmic microwave background, scientists have narrowed the possibilities down to 3. The universe could be closed like the surface of a sphere. In such a cosmos, if you could travel in a perfectly straight line, you would eventually return to your starting point, just as a ship sailing across the ocean can circumnavigate the Earth. Parallel lines would eventually converge, and the angles of a triangle would add up to more than 180 degrees. Alternatively, the universe could be open, shaped like a saddle or a Pringles chip. In this hyperbolic geometry, space curves away from itself. Parallel lines would diverge forever, and the angles of a triangle would always sum to less than 180 degrees. The third possibility is a flat universe, adhering to the classic rules of geometry we learned in school. where parallel lines never meet and a triangle's angles always equal 180 degrees. This is not about the universe being a two-dimensional sheet, but about the intrinsic curvature of three-dimensional space on the grandest scale. For decades, this was one of cosmology's great open questions. The answer came from meticulously mapping the tiny hot and cold spots in the cosmic microwave background. The size of those primordial ripples acts as a standard ruler. In a curved universe, whether closed or open, that ruler would appear distorted to our eyes, its apparent size warped by the curvature of space it traveled through. After years of analysis from satellites like WMAP and Planck, the data is unequivocal. The patterns in the ancient light show no such distortion. To an astonishing degree of precision, the universe appears to be geometrically flat. This profound flatness has a staggering implication. It tells us that the total density of the universe, the combined mass energy of everything including ordinary matter, and dark energy, is exactly at a critical value. It is perfectly balanced, like a pencil standing on its tip. If there were even a fraction more matter and energy, the universe would be closed and destined to collapse. A fraction less and it would be open, expanding into a forever thinning void. The fact that we measure it to be so perfectly flat against all odds suggests something profound about the universe's earliest moments. It points to a period of unimaginably rapid expansion in the first fractions of a second, a process called inflation, which stretched the infant cosmos so violently that any initial curvature was smoothed out to near perfection. We live, it seems, in a cosmos of exquisite geometric balance. That perfect flatness is a clue to something wild in the universe's first moments. The cosmos we see is far too uniform and balanced to have come from a simple, steady expansion. How could regions on opposite sides of the sky, billions of light years apart, have nearly identical temperatures in the cosmic microwave background? They were never close enough to exchange heat or information, not if the universe expanded at the leisurely pace we see today. This is the horizon problem. And that exquisite geometric flatness, that is the flatness problem. It is like balancing a pencil on its tip for 13 billion years without it ever falling over. The only explanation that fits is a cosmic growth spurt of unimaginable violence, a theory called inflation. For a fleeting sliver of time, perhaps from 10 to the minus 36 seconds to 10 to the minus 32 seconds after the Big Bang, the universe did not just expand. It underwent exponential expansion, inflating faster than the speed of light. The fabric of space itself stretched by a factor of at least 10 to the 26, maybe more. To grasp that scale, think of a single atom suddenly inflating to the size of our entire solar system in less than the blink of an eye. This solves the puzzles elegantly. Before inflation, the entire observable universe was a microscopic subatomic speck, a region so tiny that every part of it was in intimate contact, able to reach a uniform temperature. Then inflation happened. It took that tiny, smooth, and connected region and stretched it to a size larger than our entire visible cosmos today. The opposite sides of our sky were once neighbors, explaining their matching temperature. That violent stretching also ironed out any curvature, flattening the geometry of space like inflating a wrinkled balloon, which is why we measure a flat universe. Inflation is not just the bang in the Big Bang. It is the engine that set the stage for everything to come. It took quantum fluctuations, the tiny jitters at the smallest scales, and stretched them across the cosmos, planting the gravitational seeds that would one day become galaxies. Without this primordial frenzy, the universe might have been a formless, empty void. But if inflation stretched space itself so violently, what kind of ripples did it leave behind in the fabric of reality? The violent stretching of inflation planted the seeds for everything, but what were those seeds made of? The universe began with only the simplest ingredients. In the first few minutes after the Big Bang, a process called Big Bang nucleosynthesis took place. the cosmos was still a seething, dense soup of protons and neutrons colliding furiously in the cooling aftermath of creation. For a brief window, the temperature and pressure were just right for these particles to fuse together, but only into the lightest atomic nuclei. Nearly all the hydrogen in the universe, about 75% by mass, was forged in those first moments. Almost all the helium, about 25%, was created then too, along with trace amounts of lithium. And then the universe expanded and cooled too rapidly for anything heavier to form. For hundreds of millions of years, that was it. The periodic table consisted of just 3 entries. There was no carbon for life, no oxygen for water, no iron for blood. The cosmos was a vast, dark, and simple place. The story of how we got from that primordial simplicity to the rich chemistry of our world is written in the stars. All the elements heavier than lithium, every atom that makes up our planet and our bodies, were forged later in the nuclear furnaces of stars and in their catastrophic deaths. Inside a star's core, immense pressure and heat fuse hydrogen into helium. In later stages of a star's life, helium fuses into carbon, and carbon into heavier elements like oxygen and neon. For the heaviest elements like iron, gold, and uranium, even more extreme conditions are needed. These are created in the final moments of a massive star's life, during a supernova explosion, or in the incredible collisions of neutron stars. This means the calcium in your bones, the iron in your blood, and the oxygen you breathe were once part of a star that lived and died billions of years ago. We are quite literally made of stardust. This is a beautiful and profound connection to the cosmos. Yet, when astronomers try to take a full inventory of this ordinary matter, this baryonic matter made of protons and neutrons, they run into a baffling mystery. According to the precise measurements of the cosmic microwave background and the theory of Big Bang nucleosynthesis, we know exactly how much ordinary matter should have been created in the universe's first minutes. But when we add up all the stars, galaxies, and visible gas clouds we can detect, we find only about half of it. Billions upon billions of solar masses of atoms are simply missing. This is the missing baryon problem. Where did half the atoms in the universe go? The leading theory is that they are not in galaxies at all. They are hiding in the desolate voids between galaxies in the form of incredibly diffuse million-degree gas. This gas is so hot it emits not visible light but faint X-rays, and so thin it is nearly invisible to our telescopes. Scientists suspect this missing matter is strung along the vast filaments of the cosmic web, the dark matter scaffolding that connects galaxy clusters. These are the universe's hidden reservoirs, great rivers of hot, primordial gas that have remained almost untouched since the dawn of time. They are the lost atoms from the Big Bang, hiding in plain sight, weaving the space between the stars. This missing matter, hidden in the cosmic voids, will be the last to witness the great vanishing. The relentless acceleration driven by dark energy is not just a feature of our universe, it is a sentence for everything beyond our immediate galactic neighborhood. Galaxies will eventually vanish from our view. This is not science fiction, but a cold, mathematical certainty of our cosmic future. The expansion of space is accelerating, and that means the space between galaxy clusters is growing at an ever-increasing rate. Right now, we can see light from galaxies billions of light years away, light that left them when the universe was young. But as the expansion accelerates, a point comes where the space between us and a distant galaxy expands faster than light can travel across it. When that happens, the light from that galaxy, even light it emits right now, can never reach us. The photon is like a runner on a treadmill that is speeding up faster than they can run. They will make no forward progress. One by one, galaxies will cross this cosmological event horizon and fade from the observable universe. Their light will not just dim, it will be stretched beyond recognition. The accelerating expansion will redshift their light to longer and longer wavelengths. first from visible light to infrared, then to microwaves, and finally to radio waves of such low energy they become impossible to distinguish from the faint background noise of the cosmos. They will not explode or be destroyed. They will simply recede into a permanent silence, cut off from us by the unstoppable stretching of space itself. In the far, far future, perhaps trillions of years from now, the view from our galaxy will be profoundly lonely. The night sky, which today is sprinkled with the faint smudges of distant island universes, will go dark. The only objects left will be the gravitationally bound members of our own local group. The Milky Way and Andromeda galaxies, currently on a collision course, will have long since merged into a single, giant elliptical galaxy, which some astronomers have nicknamed Milkomda. A few dozen smaller satellite galaxies, bound by our mutual gravity, will orbit this new titan. Beyond that, there will be nothing, an endless, empty blackness. For any civilization arising in that distant epoch, cosmology would be nearly impossible. With no distant galaxies to observe, no cosmic microwave background to detect, they would have no evidence the universe ever expanded, had a beginning, or contained other islands of stars. Their entire cosmos would be their one, lonely galaxy adrift in an infinite void. The universe will have become a collection of isolated galactic islands, each forever unaware of the others, their shared history of a fiery, connected birth erased by the relentless, accelerating expansion of space. This cosmic isolation raises a chilling question about our own place in time. Our cosmic loneliness is a future written by dark energy, but its present-day behavior is creating a different kind of problem, one that threatens to crack the very foundation of modern cosmology. We call it the Hubble tension. It sounds like a minor discrepancy, a rounding error in a vast calculation, but to scientists, it is a glaring red flag. The issue is this: we have two supremely precise ways to measure the universe's current expansion rate, the Hubble constant. One method looks at the ancient universe, using the detailed map of the cosmic microwave background. By studying the subtle patterns in that baby picture, scientists can calculate how fast the universe should be expanding today, based on our standard model of cosmology. This method gives a very specific number. The other method looks at the modern universe. Astronomers use nearby stars, supernova, and other cosmic mile markers to directly measure how fast galaxies are moving away from us right now. This is a direct observation of the present-day expansion. These two methods, the ancient light and the modern motion, should agree perfectly. They are measuring the same universe after all. But they do not agree. The modern universe appears to be expanding a bit faster than the ancient light says it should be. The difference is small, only about 5 to 10%, but it is far larger than the margin of error in our measurements. This is not a mistake. It has been confirmed by multiple independent teams using different telescopes and different techniques. The tension is real, so what does this mean? A small crack in a model often reveals a much larger truth hidden beneath the surface. This tension suggests there might be something missing from our otherwise successful recipe for the cosmos. Perhaps dark energy is not a constant force but is changing over time, growing stronger. Maybe there is an unknown type of neutrino or another exotic particle from the early universe that subtly altered its evolution. Or perhaps our understanding of gravity itself needs a tweak on the largest scales. Each possibility is revolutionary. It means our cosmic story, as elegant and complete as it seems, might have an unexpected chapter we have yet to read. The Hubble tension is not a failure of science, it is science at its best, a precise measurement pointing toward a deeper mystery, a clue that the universe still has secrets to surrender. That discrepancy in the expansion rate hints at a cosmos far stranger than our models predict, and it forces us to confront the ultimate question of scale. Our best measurements tell us the universe is geometrically flat, with no detectable curvature on the largest scales we can probe. This flatness has a staggering implication. Think of the possibilities like a sheet of paper. A sheet can be rolled into a cylinder, finite but without an edge. It can be crumpled into a ball, closed and finite. Or it can extend perfectly flat in all directions, potentially forever. Our universe appears to be that third option. The lack of measurable curvature means that if you could travel in a perfectly straight line, you would never loop back to your starting point. You would just keep going. This suggests the cosmos might not just be very, very large. It might be infinite. We must separate the observable universe from the universe itself. The observable universe is our cosmic horizon, the sphere of space from which light has had time to reach us since the Big Bang. It is finite, about 93 billion light-years in diameter, and it contains everything we will ever be able to see. But that is just our island of visibility in a much larger sea. If the universe is truly infinite, then beyond our horizon, space simply continues without end. The galaxies, the cosmic web, the same structures we see around us, would stretch on limitlessly. The implications of this are almost impossible to fully grasp. An infinite universe would contain an infinite number of galaxies, an infinite number of stars, and an infinite number of planets. In such a cosmos, every possible event that has a non-zero probability of happening must happen, not just once, but an infinite number of times. Somewhere in the unobservable vastness, there could be an exact copy of our solar system, with an exact copy of Earth and an exact copy of you reading a script just like this one. There could be worlds where history unfolded slightly differently, and worlds of pure fantasy we could never conceive. This is not a claim that such copies definitely exist, but a logical consequence of infinity combined with the laws of probability. It is a concept that pushes the human mind to its very limits. We are left with a profound and haunting duality. We are trapped within a finite bubble of observation, a sphere of light and information, forever cut off from the true, possibly infinite, nature of the totality that surrounds us. All of our science, all of our telescopes, can only ever show us a single grain of sand on an endless beach. The vastness of the cosmos is not a featureless sea. Even as the universe expands, the local currents of gravity create powerful, hidden flows. Our own galaxy, the Milky Way, is not merely drifting with the cosmic expansion. It is also racing, along with thousands of nearby galaxies, toward a specific point in the sky at an astonishing speed of over 600 kilometers per second. This mysterious destination lies in the direction of the constellation Centaurus, and astronomers call it the Great Attractor. This motion is separate from and superimposed upon the grand backdrop of universal expansion. It is a local tug of war against the cosmic tide, a reminder that gravity's pull can still dominate on the scale of our galactic neighborhood. The force required to yank our entire galaxy and its neighbors in this way is immense, equivalent to the gravitational pull of tens of thousands of Milky Ways. So what is it? The leading theory is that the Great Attractor is not a single, monstrous object, but a colossal concentration of mass, a vast supercluster of galaxies, and more importantly, an ocean of dark matter. Think of it as the deepest gravitational well in our corner of the universe, a valley in the fabric of space-time toward which everything nearby is sliding. The frustrating part is that we cannot see its heart. The core of this immense gravitational anomaly lies almost directly behind the crowded, dusty plain of our own Milky Way galaxy. From our vantage point, we are trying to peer into the heart of a distant city while standing in a dense, luminous fog. Our view in visible light is completely obscured by the stars, gas, and dust of our own galactic disk. This zone of avoidance, as astronomers call it, has long hidden the true nature of the Great Attractor. To uncover its secrets, scientists have had to use other tools. By meticulously mapping the motions of thousands of galaxies around us, they can trace the gravitational flows like watching leaves swirl in a river to find the waterfall. Observations in radio and X-ray wavelengths, which can penetrate the galactic dust, have begun to reveal the structure. We now believe the Great Attractor is part of an even larger congregation of mass known as the Laniakea supercluster, of which our own local group is just a distant suburb. At its center lies the Norma cluster, a dense knot of galaxies, but even that may not be the full source of the pull. The true engine is likely the unfathomable amount of dark matter saturating this region of space, a hidden mountain range of gravity bending the paths of entire galaxies. It is a humbling reminder that even as we map the universe's grand expansion, powerful, unseen currents still flow in the darkness, guiding our cosmic journey. That faint, cold glow from the dawn of time is more than just ancient light. It has a specific, measurable temperature. The cosmic microwave background radiation is not just random static. It has what physicists call a nearly perfect blackbody spectrum. This is a specific fingerprint of an object in perfect thermal equilibrium, emitting radiation purely because of its heat. A common example is the glow from a hot piece of metal, like the filament in an old light bulb. The spectrum of that glow has a distinctive shape that depends only on the object's temperature. The CMB has that exact same perfect shape. When we measure it with extraordinary precision, we find its spectrum corresponds to a temperature of 2.725 Kelvin. That is just 2.725 degrees above absolute zero, the coldest possible temperature where all molecular motion stops. In more familiar terms, it is about -270.4 degrees Celsius. This is not the temperature of a place, it is the temperature of space itself. This frigid chill is the leftover heat from the Big Bang, stretched and cooled over 13.8 billion years of expansion. It is the cosmic baseline, any patch of deep space far from the warming influence of any star or galaxy will eventually radiate away its own heat and settle to this fundamental temperature. The void between galaxies is not just empty and dark, it is profoundly cold, kept just a few degrees above absolute zero by the fading embers of creation. This uniform temperature blankets the entire observable universe, a final, chilling whisper of that initial fire. But if the universe has a temperature and it is expanding and cooling, what does that tell us about its very first moments? That frigid whisper of the Big Bang is not silent. It carries a tone, a resonance from the universe's first moments. The cosmic microwave background, that uniform sea of microwave light, is imprinted with a pattern of faint hot and cold spots. But these are not random. They are the fossilized imprint of sound waves, the echoes of a cosmic symphony that played for the first 380,000 years of the universe's life. Before the cosmos became transparent, it was a dense, seething plasma, a fluid of light and matter. In this primordial soup, gravity pulled matter inward, trying to collapse it, while the intense pressure of the trapped light pushed it back outward. This push and pull created oscillations, ripples of compression and rarefaction that traveled through the plasma like sound waves through air. These were literal sound waves in the medium of the early universe, but on a scale so vast it defies comprehension. The waves traveled at over half the speed of light, ringing out across the infant cosmos. Then, at the moment of recombination, when atoms formed and the fog lifted, the music stopped. The waves froze in place, their peaks and troughs captured as slightly denser and slightly less dense regions in the newly transparent gas. These are the hot and cold spots we see in the CMB map today. By meticulously measuring the size and distribution of these spots, cosmologists can decode the harmonics of that ancient sound. It works much like how a musical instrument has a fundamental note and overtones that reveal its shape and material. The early universe, acting like a gigantic resonant cavity, had a specific set of preferred wavelengths for these sound waves. The most common or fundamental wavelength is the distance a sound wave could travel from the Big Bang until the moment the music stopped. We see this scale imprinted as a characteristic size for the hotspots in the CMB. but we also see the overtones, the harmonics. The data reveals a series of peaks and valleys in what is called the power spectrum, a graph of how common different-sized ripples are. The precise position and height of these peaks are a treasure trove of information. They tell us the composition of that primordial plasma, the ratio of ordinary matter to dark matter, the overall density of the universe, and even confirm the flat geometry of space. The first peak confirms the flatness. The second peak's height is exquisitely sensitive to the density of ordinary matter, telling us how much baryonic stuff was in the soup. The third peak reveals the influence of dark matter, which did not interact with the light but whose gravity shaped the waves. This acoustic analysis is so precise it allows us to hear the universe's first chord, and from that single chord, deduce the entire orchestral score of its contents and history. It is the most powerful evidence we have for the standard model of cosmology, a direct listen to the vibrations of creation itself. That symphony of sound waves from the infant cosmos reveals a profound underlying order. It tells us that despite the magnificent complexity of galaxies and voids we see today, the universe follows a simple, elegant rule on the grandest scale. This rule is called the cosmological principle, and it is the bedrock upon which all of modern cosmology is built. It makes two powerful statements about the nature of the cosmos. First, the universe is isotropic. This means it looks the same in every direction you look. From our vantage point, we see galaxies, clusters, and vast voids stretching out in all directions, with no single privileged axis or special direction. The cosmic microwave background glow is the ultimate proof of this. Its temperature uniform to within 1 part in 100,000 across the entire sky. The second statement is even more profound. The universe is homogeneous. This means that on the largest scales, it looks the same from every location. The distribution of matter and energy is roughly even when you zoom out far enough. This is a much harder claim to verify because we are stuck here on Earth. We cannot instantly travel to a galaxy a billion light-years away and look back to see if the view matches our own. Yet everything we observe supports this idea. Deep galaxy surveys show that while our local neighborhood has clusters and filaments, if we average over volumes hundreds of millions of light-years across, the density of galaxies evens out. The universe, in its grand architecture, has no unique center and no edge. There is no special place. This principle is why we can talk about a universal history with confidence. It allows us to assume that the laws of physics we measure here, gravity, electromagnetism, nuclear forces, operate in exactly the same way in a galaxy 10 billion light-years away. Without this assumption, cosmology would be impossible. We could not extrapolate from the light of distant supernova or the patterns in the ancient microwave background to understand the cosmos as a whole. The cosmological principle transforms the universe from an incomprehensibly vast and unique place into something we can actually study scientifically. It gives us permission to believe that our local observations are a fair sample of the whole. Of course, this principle only holds true on the very largest scales. It clearly breaks down locally. Our planet orbits a star in a specific galaxy within a specific cluster. We are in a very special place for life, but we are in no way a special place in the geometry of the cosmos itself. From any other galaxy in the universe, the large-scale view would be statistically identical. A roughly even sea of galaxy clusters stretching into the distance, with a uniform microwave glow filling the sky. This foundational idea of a uniform cosmos leads directly to a haunting and beautiful prediction about our ultimate cosmic address. The echoes of that primordial symphony are not confined to the faint microwave glow. They are permanently stamped into the large-scale structure of the universe itself, providing us with one of the most powerful measuring tools in all of cosmology. These are the baryon acoustic oscillations, the BAOS, and they act as a cosmic ruler of known length etched across the heavens, to understand this, we need to return to those sound waves ringing through the early plasma. When the music stopped at recombination, the waves froze. The peaks of those waves, the regions of slightly compressed matter, were the seeds for future galaxy formation. But here is the crucial part. Each wave left a characteristic imprint. Picture a single ripple in a pond, frozen at the moment it reaches its maximum size. At the center of that ripple is the densest point, the original seed. But the ripple itself has a specific radius, the distance the sound wave traveled before the universe became transparent. This distance, about 500 million light-years in today's expanded universe, became a preferred scale for structure. When galaxies finally formed billions of years later, they did not form just at the original seed points. They also had a slight statistical tendency to form at that specific ripple's edge. The result is that when we map the positions of millions of galaxies in the universe today, we find a subtle but detectable signal. Galaxies are slightly more likely to be separated by this specific scale, about 500 million light-years, than by any other distance. It is as if the universe is imprinted with a faint, repeating pattern, a cosmic fingerprint where the spacing between the walls is always the same. This is the standard ruler. We know its true size from our understanding of the physics of the early universe and from the precise measurements of the CMB. Now, here is where it becomes a tool for measuring expansion. When we look out into the universe, we see it at different epochs. Light from a galaxy 1 billion light-years away shows us the universe as it was 1 billion years ago. Light from a galaxy 7 billion light-years away shows us the universe as it was 7 billion years ago. By measuring the apparent size of this standard ruler, the BO scale, at these different distances or redshifts, we can see how it has been stretched by the expansion of space over cosmic time. If the expansion has been steady, the ruler will appear stretched by a predictable amount. If the expansion accelerated or decelerated at certain times, the apparent stretching will be different. By conducting enormous galaxy surveys like the Sloan Digital Sky Survey, astronomers have measured this BO signal with incredible precision. They can see how that 500 million light-year ruler appears when the universe was half its current age and when it was only a quarter of its current age. Each measurement is a data point on the graph of cosmic expansion, allowing us to trace the history of how the universe has stretched over billions of years. It provides independent, robust confirmation of the acceleration driven by dark energy and helps pin down the precise values of the universe's ingredients. It is a direct link between the sound waves of the infant cosmos and the galactic architecture of the present, a fossilized echo we can use to measure the growth of space itself. The fate written by dark energy is a slow, cold, and inevitable dissolution. This ultimate destiny is often called the heat death or the big freeze. It is not a dramatic cataclysm, but a gradual fading into a state of perfect stillness. The accelerating expansion will continue to push galaxies beyond the cosmic horizon, isolating every gravitationally bound group in its own private, shrinking island of light. Within these isolated galaxies, the story is one of fuel running out. Stars, the engines of light and energy, will one by one exhaust their nuclear fuel. Massive stars will end in supernova, leaving behind neutron stars or black holes. Smaller stars like our Sun will swell into red giants and then collapse into fading white dwarfs. Over trillions of years, the process of star formation will cease entirely as the interstellar gas needed to make new stars is either consumed or expelled. The galaxies will darken. The last red dwarf stars, which burn their fuel with miserly slowness, will finally flicker out after perhaps 10 trillion years. The cosmos will be left with the stellar corpses, cooling white dwarfs that glow with a dim, residual heat, neutron stars and black holes. In this near-perfect darkness, gravity will still work its slow magic. Occasionally, over incomprehensible spans of time, stellar remnants will collide, perhaps producing a final, rare flash in the eternal night. but even these events will become vanishingly rare as the expansion pulls everything usefully apart. The final chapter belongs to the black holes themselves and a process predicted by Stephen Hawking. Black holes are not truly eternal. Through a subtle quantum effect at their event horizons, they are theorized to slowly leak radiation, losing mass in what we call Hawking radiation. For a black hole with the mass of our Sun, this evaporation would take longer than the current age of the universe to even begin to be noticeable. For the supermassive black holes at the centers of galaxies, the timescale is staggering, on the order of 10 to the 100 years, a number so vast it has no meaningful analogy. But given enough time, even these cosmic titans will evaporate in a final, faint burst of particles, and after that, nothing. The universe will approach a state of maximum entropy. This is a thermodynamic term for the ultimate level of disorder, where energy is uniformly spread out and no gradients exist, no hotspots, no cold spots, no differences that can be harnessed to do work. It will be a vast, homogeneous, and isotropic sea of nearly identical particles and radiation, so thinly spread and so low in energy that effectively nothing happens. Ever again, there will be no light, no structure, no change, just a perpetual, frozen equilibrium in an ever-expanding void. This is the big freeze, the universe achieving a perfect and perfectly lifeless uniformity. The big freeze is our most likely future, but cosmology must always consider the extremes. What if dark energy is not a constant, gentle push, but a force that grows stronger over time? This possibility leads to a fate far more violent than a slow fade, the Big Rip. In this scenario, dark energy would be a form of phantom energy with a repulsive strength that increases as the universe expands. Instead of simply pushing galaxies apart, its influence would eventually overcome every binding force in nature, from the largest scales down to the smallest. First, the accelerating expansion would shred the cosmic web, tearing galaxy clusters apart. Then it would rip individual galaxies from themselves, flinging stars into the void. As the phantom energy grows unimaginably strong, it would attack the stars and planets themselves. A star like our Sun would be torn apart when the repulsive force between its atoms exceeds the gravity holding it together. Next, planets would disintegrate. Finally, in the last instance, the phantom energy would overcome the nuclear forces holding atomic nuclei together, and then the forces binding quarks within protons and neutrons. The very fabric of space-time would rupture at a single, finite moment, tearing every fundamental particle away from every other. The universe would end not with a whimper, but with a catastrophic, instantaneous dissolution of reality itself. It is a theoretical possibility, but current measurements of dark energy's behavior over the last several billion years show it to be remarkably consistent, like a true cosmological constant. This consistency strongly disfavors the phantom energy needed for a big rip. The opposite extreme is equally dramatic but stems from a different cosmic balance. What if the expansion were to slow, halt, and reverse? This is the Big Crunch, a mirror image of the Big Bang. In this model, the collective gravity of all the matter and dark matter in the universe is sufficient to eventually overcome the expansion. The galaxies would slow their recession, stop, and then begin rushing back toward each other. As they converge, the universe would heat up. The cosmic microwave background would blue shift back into a searing glow. Galaxies would merge in catastrophic collisions, stars would be torn apart, and space itself would compress. Eventually, all matter and energy would be driven back into a singularity of infinite density and temperature, a fiery end that could, in some speculative theories, trigger a new Big Bang and another cycle of creation. This cyclical universe is a compelling idea, but it requires a very specific density of matter. Our most precise measurements tell us the universe is geometrically flat, meaning its total density is at the critical value. However, that density is dominated by dark energy, which acts as repulsion, not attraction. For a big crunch to occur, dark energy would need to decay away or reverse its nature, and the density of attractive matter would need to be much higher. Our inventory of the cosmos shows this is not the case. The acceleration we observe is the definitive evidence against a future collapse. So why does the Big Freeze or heat death remain the leading forecast? Because the data we have, the consistent behavior of dark energy, the flat geometry, and the measured acceleration, all point to a universe that continues to expand and cool forever, diluting into maximum entropy. It is the future written by the numbers, a slow-motion vanishing act on a cosmic stage that grows darker and quieter with each passing eon. Yet, even this seemingly settled picture holds one final, profound uncertainty, a question that reaches back to the very beginning of everything. This fundamental truth redefines our place in the cosmic story. We are not passive spectators watching the universe expand from some detached balcony. We are active participants woven into the very fabric that is stretching. The expansion of the universe is not something happening out there beyond some invisible barrier. It is happening here within the space you occupy right now. The same stretching that carries distant galaxies apart is also operating in the room around you and even within the atoms of your own body. This is a difficult perspective to internalize because we do not feel ourselves being pulled apart. The reason is a cosmic tug of war happening at every scale. While the expansion of space acts everywhere, its effect is incredibly weak over small distances. It is a faint background force. In our local environment, it is utterly dominated by other, much stronger forces. Gravity holds our solar system together, binding Earth in its orbit around the Sun. Electromagnetism binds atoms into molecules, and molecules into the chair you are sitting on and the device you are holding. The nuclear forces hold atomic nuclei together with immense strength. These local forces are so powerful that they completely overpower the minuscule stretching of space on human, planetary, and even galactic scales. Think of it like a tiny, gentle breeze trying to pull apart a skyscraper held together by steel beams and concrete. The breeze is real, but its effect is negligible against the structural integrity of the building. So, while the space between the nuclei and electrons in your atoms is technically subject to cosmic expansion, the electromagnetic force holding them together is trillions upon trillions of times stronger. You are not expanding, the Earth is not expanding, the solar system is not expanding. These are all gravitationally bound systems, islands of stability within the grand, flowing river of expanding space. The expansion only becomes the dominant force in the vast, empty deserts between galaxies, where gravity's grip is weak and the distances are so colossal that the tiny stretching per mile adds up to a phenomenal recession. To truly see the expansion at work, you must look beyond your local galactic neighborhood, out to where the fabric of space itself is the main character in the story. This embedded perspective is humbling and illuminating. We are not outside the universe looking in. We are of the universe experiencing its history from within, carried along on the stretching canvas of reality itself. That embedded perspective of being within the universe raises a startling possibility. What if our entire cosmos, from its first moments of inflation to its eventual heat death, is not the whole story? What if it is just one island in an infinite archipelago of realities? This leads us to the most speculative yet philosophically profound consequence of our leading theories. It is the idea of the multiverse. According to some models of cosmic inflation, the violent stretching that smoothed and flattened our early universe may not have been a one-time event. Instead, it could be a perpetual, eternal process. In this picture, the inflating field of energy that drove our universe's growth does not switch off everywhere at once. Think of a pot of water coming to a boil. Bubbles form, expand, and rise to the surface. In eternal inflation, our universe is one such bubble. It is a region where inflation locally ended, allowing for the formation of stars, galaxies, and us. But outside our bubble, the inflating sea of primordial energy continues to expand at an unimaginable rate. In that eternally inflating background, new bubbles, new universes are constantly nucleating, popping into existence with their own random properties. Each of these bubble universes would be causally disconnected from all others, forever separated by oceans of hyper-inflating space that expands faster than light can cross it. They are not parallel worlds in another dimension. They are separate space-times, each with its own Big Bang and potentially its own unique set of physical laws. This is where the idea becomes truly mind-bending. The fundamental constants of our universe seem finely tuned for complexity. If the strength of gravity were slightly different or the nuclear forces a bit weaker, stars would never form, chemistry would be impossible, and life could not arise. Why do we live in such a seemingly tailored cosmos? The multiverse offers a controversial answer. In an eternally inflating sea, every possible variation of physical constants would be realized in some bubble universe. Most of those universes would be stillborn, empty, or fleeting, but a tiny fraction, by pure random chance, would have the precise cocktail of laws that allow for galaxies, planets, and observers. We, by necessity, find ourselves in one of those rare, habitable bubbles. It is not that the universe was made for us, but that we are a product of its rare, viable conditions. This is not proven science. We have no way to observe or communicate with other bubble universes. They exist beyond our cosmic horizon forever. Yet, the multiverse is not pure fantasy. It emerges naturally as a theoretical implication of our most successful model of the early universe, inflation. It is a staggering reminder that the ultimate nature of reality may be far grander and stranger than the single, expanding cosmos we call home. The multiverse remains a breathtaking possibility, but our journey through the cosmos always returns us to the single, magnificent reality we can actually measure. The 25 astounding facts we have explored, from the stretching of light to the echoes of ancient sound, form the pillars of our current understanding. They reveal a universe that is dynamic, vast, and filled with structure born from a fiery beginning. Yet, this elegant model, for all its predictive power, is not a finished story. It is a map with vast, blank regions labeled "Here be dragons." The true nature of dark energy and dark matter, the persistent puzzle of the Hubble tension, and the ultimate origin of the Big Bang itself, these are not minor details. They are fundamental gaps in our comprehension of reality. They remind us that every answer we uncover simply leads to deeper, more profound questions. This is not a failure of science, but its very essence. The quest for understanding is not ending. It is accelerating, fueled by a new generation of tools designed to peer into the darkness. Soon, the Nancy Grace Roman Space Telescope will launch, its wide-field gaze designed to chart the influence of dark energy across cosmic history with unprecedented detail, seeking to understand if its repulsive force has changed over time. On a mountaintop in Chile, the Vera Sea, Rubin Observatory will begin its legacy survey of space and time, scanning the entire southern sky every few nights. It will discover billions of new galaxies and map the cosmic web in finer detail than ever before, while also hunting for the subtle gravitational effects of dark matter and searching for clues to the expansion rate discrepancy. These missions and others like them will gather oceans of new data. They will measure the universe's growth, trace its structure, and listen for whispers from its dawn with a precision we can scarcely imagine today. Some mysteries may surrender to this onslaught of observation. Others will undoubtedly deepen, revealing new layers of cosmic strangeness we have not yet even conceived. The expanding universe is not a solved puzzle. It is an ongoing conversation between human curiosity and the profound, whispering cosmos, a dialogue that is just beginning to find its voice. Our cosmic journey has taken us from a simple reddening of starlight to the edge of reality itself. We followed Edwin Hubble's discovery that galaxies are fleeing, not through space, but with the stretching of space, a revelation that pointed directly back to a fiery beginning. We witnessed the afterglow of that birth in the cosmic microwave background, a frigid whisper that carries the blueprint for all galaxies. We then met the universe's hidden architects, dark matter, whose invisible scaffold holds the cosmic web together, and dark energy, the mysterious force now accelerating the expansion, pushing galaxies beyond a horizon of eternal silence. This is not a static picture hanging in a museum. It is a movie still playing with a plot written into the very fabric of existence. We live in a cosmos that had a dramatic beginning, that built immense structures from quantum whispers, and that is now racing toward a future of profound isolation and cold. The fate of everything is inextricably tied to this relentless, accelerating stretch. Tonight, when you look up at the stars, remember you are not looking at a fixed canopy. You are seeing history. Each point of light is a message from a different chapter in this grand story. A story of expansion that encompasses everything from the first spark to the last fading ember. Let that knowledge transform a simple glance into an act of cosmic time travel. Which of these 25 facts reshaped your view of the universe the most? Share your moment of wonder in the comments below, and if you are hungry for more mysteries, subscribe to continue the adventure. The universe still has countless secrets waiting to be told.